exercise you shall be able to connect, start, run, and build up the voltage of an alternator. Connect the resistive, inductive load to the three-phase alternator. Determine the voltage regulation of an alternator. Tools, instruments. Combination pliers 200 mm, 1 number. Round nose pliers 150 mm, 1 number. Electrician's knife, 1 number. Moving ion ammeter 0 to 20 amps, 3 numbers. Moving ion voltmeter 0 to 500 volts, 1 number. Moving coil ammeter 0 to 5 ampere, 1 number. Frequency meter 500 volts, 45 to 55 Hz, 1 number. Single phase power factor meter 500 volt, 0.5 lagging to 0.5 leading, 1 number. Tachometer 300 to 3000 RPM, 1 number. Equipment, machines. 3-phase alternator 500 volts. 5 or 10 kW coupled with DC shunt motor having facility for speed control, 1 set. 3-phase lamp load 415 volt, 5 kW, 1 number. 3-phase squirrel cage motor 500 volt 50 Hz, 3 HP with DOL starter and switch, 1 number. Materials. PVC insulated stranded aluminum cable 10 meters. Triple pole ion-clad switch 32 amps 500 volts, 2 numbers. Task 1. Connect, start, run, and build up the voltage of an alternator. Note down the nameplate details of the given alternator in Table 1. Select proper sizes of cables, fuse wires, switches, etc. Connect the exciter output terminals to the field of the alternator with the rheostat, ammeter and voltmeter. Connect the alternator terminals RYB and N to the load as per the circuit diagram. Keep the load switches and also all the lamp switches of the lamp load in the off position. Run the alternator at its rated speed. Measure and record the speed. Build up its voltage by adjusting the field rheostat to the rated voltage of the alternator. Read and record it. Task 2. Load a 3-phase alternator with a resistive load. Close the TPIC switch of the lamp load and note down the values of the load current, which will be 0, the terminal voltage, power factor and frequency in Table 2. Slowly increase the load current to 1 amp by switching on the lamps one by one. Increase the load current equally on all the 3 phases of the alternator to its rated value by switching on the lamps in steps of 1 amp. For each step, note down the current, voltage, and the power factor frequency and tabulate the readings in Table 2. Reduce the load gradually to 0. Open the lamp load by switching off the TPIC switch. . Task 3. Load a 3-phase alternator by a 3-phase motor, inductive load. Close the TPIC of the motor load and start the motor by the DOL starter. Read and record load current, terminal voltage, power factor and frequency in Table 3. Switch off the TPIC, switch off the motor load. Task 4. Determine the voltage regulation of an alternator. Close the TPIC, switch off the motor load and start the motor by the DOL starter. Close also the TPIC, switch off the lamp load and increase load current up to the alternator's rated value in steps of 1 ampere. Read and record the values of load current, terminal voltage and power factor frequency in Table 4. Reduce the load and switch off the alternator. Draw the 3 curves for the 3 sets of reading as recorded in Tables 2, 3 and 4 in the same graph showing the terminal voltage versus load current. Keep the terminal voltage in the y-axis and load current in the x-axis. Compare the power delivered to the resistive, inductive, partially resistive, resistive inductive loads with the corresponding line current and line voltage and power factor at least 3 different line current values. Calculate the voltage regulation for the above different loads at 5 and 10 amperes by using the formula percentage voltage regulation %VR. Voltage regulation in percentage equal to no load voltage minus full load voltage by full load voltage into 100. Based on the previous steps, the conclusion for 5 and 10 amperes. Task 1. Connect, start, run, and build up the voltage of an alternator. Note down the nameplate details of the given alternator in Table 1. Connect the exciter output terminals to the field of the alternator with the rheostat, ammeter, and voltmeter. Connect the alternator terminals RYB and N to the load as per the circuit diagram. Keep the load switches and also all the lamp switches of the lamp load in the off position. Run the alternator at its rated speed. Measure and record the speed. Build up its voltage by adjusting the field rheostat to the rated voltage of the alternator.
Now you have learned to connect, start, run and build up the voltage of an alternator. Connect the resistive inductive load to the three-phase alternator. Determine the voltage regulation of an alternator. Hope you had a clear understanding on this technical process. Thank you.
Parallel operation and synchronization of three-phase alternators.
Hello everyone. Today we'll be looking at the process of electrician practical session for parallel operation and synchronization of three-phase alternators.
Objectives. At the end of this exercise you shall be able to read and interpret the nameplate details of the two three-phase alternators. Synchronize the two three-phase alternators by dark lamp method and test it. Synchronize the two three-phase alternators by dark and bright lamp method and test it. Synchronize the two three-phase alternators by synchroscope method and test it. Tools Instruments. Trainees Toolkit 1 number. Moving ion voltmeter 0 to 500 volt 2 numbers. Frequency meter 45 to 55 Hz 1 number. Phase sequence indicator 1 number. Synchroscope. Equipment machines. Three-phase alternators 5 kV by 500 volt 50 Hz coupled with prime mover adjustable speed control. Rheostat 150 ohms 1 ampere 1 number. Materials. TPIC switch 16 ampere 500 volt. Ion-clad double-pole switch 16 ampere to 50 volt 1 number. Ion-clad triple-pole switch 16 ampere 500 volt 2 numbers. 100 watt 250 volt lamps 6 numbers. Connecting wires. Task 1. Read and interpret the nameplate details of the alternators. Read and interpret the nameplate details of the three-phase alternator. Note down the details of alternators in Table 1. Task 2. Synchronize the two three-phase alternator by dark lamp method and test it. Check the phase sequence of the main bus bar line by using phase sequence indicator meter. Connect and set the arrangement of incoming alternator and outgoing alternator with prime mover coupled TPIC main switch, voltmeters and frequency meters and lamp connection in series. Keep the main switch of incoming alternator 1 in closed position after ensuring the phase sequence are correct. Keep the main switch of alternator 2 in opened position. Start and run the first alternator and build up the rated voltage. Measure the line voltage between phases, then measure the frequency of an alternator 1 and note down the readings of voltmeter and frequency meters in Table 2. Start, run and build up the rated voltage. Measure the line voltages and frequency in alternator 2 and note down the readings in Table 3. Check the condition of the two lamps. If the voltage and frequency are equal, the lamps will becomes dark and then becomes bright. If the voltage and frequency of the both alternators are not same, the lamps will flicker. Adjust the field excitation current in the alternator to and bring the voltage to the same value of the alternator 2. Check the condition of lamp's brightness. If the lamps are flickering still now, then the frequency may not be equal. It must be brought to same equal frequency value of alternator 1. Adjust the speed of the prime mover of alternator 2 and bring the frequency as same as in alternator 1. Now, all the lamps are bright and then become dark at a time. It indicates all the conditions are fulfilled for synchronizing. Close the main switch of alternator to when all the lamps are in dark condition. Switch on common load for both the alternators. Check the loads are shared equally by the two alternators. Get it checked with your instructor. Task 3. Synchronize the two three-phase alternators by dark and bright lamp method. Check the phase sequence of the main bus bar lines by using phase sequence indicator. Connect and set up the arrangement of the alternator 1 and alternator 2 with prime mover, TPIC switch, lamp connection. Two pairs of lamp are connected across two phases. In one phase, the pair of the lamps are in series with voltmeters and frequency meters. Keep the main switch of alternator 2 in opened position. Start and run the first alternator and build up the rated voltage. Measure the line voltage between phases, then measure the frequency of an alternator 1 and note down the readings of voltmeter and frequency meters in table. Note down the readings in table 4 and table 5. Look at the condition of the lamps. If the voltage and frequency are equal, then one pair of the lamp will be dark and other two pair will be bright. If the voltage and frequency of the both the alternators are not same, then the lamp will flicker, not giving standstill lighting. Check the voltage and frequency are not equal. Repeat the steps of task 2 and bring the same value of voltage and frequency as in alternator 1. If all the conditions are fulfilled, then all the lamps will not flicker and one pair of the lamp will be dark and other two pair lamps will be bright at a time. Close the main switch of alternator to when the lamps are bright condition. Switch on the common load for both alternators. Check the loads are shared equally by the two alternators. Task 4. Connect two alternators in parallel by using synchroscope. Collect the instruments as shown. Connect the equipment and instruments. Start the incoming alternator 2, with low excitation. Close the bus bar switch S1. Observe the bus bar voltage V1 and incoming voltage V2. Adjust the excitation of the incoming alternator till V1 equal to V2. The voltage of incoming and exciting machine should be equal. Check the pointer in the synchroscope. Adjust the speed of the alternator. If it is indicating fast, reduce the speed of the incoming machine gradually, observing the synchroscope pointer. Adjust the speed of the incoming alternator for minimum oscillation of the synchroscope pointer. Close the synchronizing switch S2 at 0 and the steady position of the synchronizing pointer.
Now you can read and interpret the nameplate details of two three-phase alternators. Synchronize the two three-phase alternators by dark lamp method and test it. Synchronize the two three-phase alternators by bright and dark lamp method and test it. Synchronize the two three-phase alternators by synchroscope method and test it. Hope you had a clear understanding on this technical process. Thank you.
Connect start and plot V-curves for synchronous motor under different excitation and load conditions.
Hello everyone. Today we will be looking into the process of electrician practical session to connect, start and plot V-curves for synchronous motor under different excitations and load conditions.
Objectives. At the end of this exercise you shall be able to connect the synchronous motor with its starter. Start and run the synchronous motor with its starter. Plot the V-curve. Tools Instruments. Trainees Toolkit 1 number. Moving ion ammeter 0 to 10 ampere 1 number. Moving coil ammeter 0 to 1 ampere 1 number. Moving ion voltmeter 0 to 500 volt 1 number. Frequency meter 45 to 55 Hz 1 number. Tachometer 0 to 10,000 RPM 1 number. Equipment machines. Synchronous motor 3 kV, 500 volt 3 phase 50 Hz with suitable starter 1 number. DC source suitable for the given synchronous motor 1 number. PPIC switch 32 ampere 500 volt 1 number. DPIC switch 16 ampere to 50 volt 1 number. Field rheostat suitable for above motor 1 number. Materials. Connecting leads as required. Task 1. Connect the synchronous motor, start, run and test it. Make the connections as per circuit diagram. Show the connections to your instructor and get his approval. Close TPIC switch and DPIC. Adjust the field current to its rated value as per nameplate detail. Hold push button S2 depressed and start the motor by operating switch S1. Make sure that push button S2 is pressed before energizing the motor at the time of starting. When S2 is depressed, DC supply to field is disconnected and field winding terminals F1 and F2 are shorted. After the rotor attains maximum speed, say 95% of the synchronous speed, release push button S2, that is, field winding is excited by DC supply. With field winding excited, the motor gets pulled into synchronism and runs at synchronous speed. Measure speed, supply voltage, frequency, line current, and field excitation current and record in Table 2. Calculate the synchronous speed of the motor by using the formula. Compare the synchronous speed with the measured speed and ensure measured speed is equal to synchronous speed. Task 2. Plot the V-curve for synchronous motor under different excitation and load condition. Start and run the synchronous motor to its maximum speed without load. Adjust the field current by adjusting the field rheostat and take the readings of armature current and field current. Note down the readings in Table 1 and plot the V curves for synchronous motor under different excitation and load conditions in a separate graph sheet. The same procedure has to be repeated for loaded condition.
Now you have learnt to connect the synchronous motor with its starter. Start and run the synchronous motor with its starter. Plot the V curve. Hope you had a clear understanding on this technical process. Thank you.
Identify the parts and terminals of motor generator set.
Hello everyone. Today we'll be looking at the process of electrician practical session to identify the parts and terminals of MG set.
Objectives: at the end of this exercise you shall be able to read and interpret the nameplate details of the given MG set. Determine the pairs of terminal of the windings of the DC machine by the test lamp method. Identify their parts and write their names. Tools: instruments. Insulated combination pliers 200 mm, 1 number. Screwdrivers 150 mm, 1 number. DE spanner set 1 number. Equipment: machine. 3-phase squirrel cage induction motor, 5 horsepower, 500 volts, 50 Hz, with star delta starter. DC shunt generator 5 kilowatts 220 volts with field regulator, 1 number. Materials: PVC insulated cable, 320 or 660 volts, grade 5 meters. Kit Kat fuse to 50 volt 16 ampere, 1 number. Pendant lamp holder to 50 volt 6 ampere, 1 number. Single pole switch, 1 number. DC lamp 40 watts to 50 volts, 1 number. Fuse wire 5 amp. As required. Task 1. Identify the parts and terminals of motor of AMG set. Read and interpret the nameplate details of the given 3-phase squirrel cage induction motor and note down as on Table 1. Table 1. Nameplate details. Identify the parts of AC squirrel cage induction motor from the real object or from the exploded view chart. Fan guard. Fan. End shield. End shield. Shaft. Terminals box. Rotor. Stator. Bearing. Label the each parts with number and write then name of parts. Table 2. Rotor and shaft. Fan. Fan guard. Stator, frame and terminals box. End shield. Bearing. Task 1. Identify the parts and terminals of a 3-phase induction motor. Video procedure. Read and interpret the nameplate details of the given 3-phase squirrel cage induction motor and note down as on Table 1. Identification of the terminals of an induction motor, 3-phase. Identify the terminals of a 3-phase induction motor with the help of two lamps in series. Observe the condition of the lamp and write the name of terminals. If the lamps glow bright as shown in the figure, then the linked ends are similar ends. For example, the linked end are U1 and V1. If the lamps glows dim as shown in figure, then the linked ends are dissimilar ends. For example, the linked end are U1 and V2. Task 2. Identify the terminals of DC generator of the MG set. Read and interpret the nameplate details of the given DC generator and note down in Table 2. The terminals where the lamp glows more brightly belong to the series field winding. The terminals where the lamp glows dimly belong to the shunt field winding, and the terminals where the lamp glows brighter belong to the armature terminals. Write down the terminal name of DC generator.
Now you have learned to read and interpret the nameplate details of the given MG set. Determine the pairs of terminals of the windings of the DC machine by the test lamp method. identify their paths and write their names. Hope you had a clear understanding on this technical process. Thank you.
Start and load a NG set with 3-phase induction motor coupled to DC shunt generator.
Hello everyone. Today we'll be looking at the process of electrician practical session to start and load a MG set with 3-phase induction motor coupled to a DC shunt generator.
Objectives: at the end of this exercise you shall be able to connect 3-phase motor with the starter, connect a DC shunt generator, field regulator, ammeter and voltmeter, start the 3-phase AC motor, adjust the field regulator and build up DC voltage, determine combined efficiency of the MG set. Tools, instruments: electrician toolkit 1 set, moving ion voltmeter 0 to 500 volts 1 number, moving ion ammeter 0 to 15 ampere 1 number, moving coil ammeter 0 to 2.5 ampere 1 number, moving coil ammeter 0 to 15 ampere 1 number, moving coil voltmeter 0 to 250 volts 1 number, power factor meter 500 volts, 15 ampere, 0.5 lagging to 0.5 leading 1 number, tachometer multi-range 0 to 3000 rpm 1 number. Equipment, machines: 3-phase squirrel cage induction motor, 5 HP, 500 volts, 50 Hz with star delta starter, 500 volts, 16 ampere 1 number, DC shunt generator 5 kilowatts to 20 volt with field regulator 1 number, lamp bank of 5 kilowatts 250 volt 1 number. Materials: ICTP switch 16 ampere 500 volt 1 number, lamp holder pendant 2 numbers, lamp to 50 volt 60 or 100 watts bulb 2 number, stranded PVC insulated wire 7 1.5 cable, DPST switch 16 ampere to 50 volt 1 number, PVC insulated connecting cable, ICDP switch 16 ampere to 50 volt 1 number. Task 1: start, run and load a MG set. Connect the AC motor and generator. Start the AC motor. Measure the speed using a tachometer. Build up the DC generator terminal voltage to its rated value and observe the voltmeter V2 reading. Switch on the load switch S2. Increase the load gradually by switching on the lamps in steps up to the rated capacity of MG set. Measure the speed of the generator for each load condition and record in Table 1. Record input current, voltage and power factor in Table 1. Read and record the load current and terminal voltage of generator in Table 1. Switch off the load in steps and open the load switch S2. Calculate the input power. Calculate the output power. Calculate the total loss and the efficiency at full load. Stop the prime mover of the MG set and isolate supply. Task 1. Start, run, and load a MG set. Connect the AC motor and generator. Start the AC motor. Measure the speed using a tachometer. Build up the DC generator terminal voltage to its rated value and observe the voltmeter V2 reading. Keep the field regulator at a position to include zero resistance in the circuit. Keep switch S1 and S2 in off position. Switch on the load switch S2. Increase the load gradually by switching on the lamps in steps up to the rated capacity of MG set. Measure the speed of the generator for each load condition and record in Table 1. Record input current, voltage and power factor in Table 1. Read and record the load current and terminal voltage of generator in Table 1. Stop the prime mover of the MG set and isolate supply. Conclusion: the terminal voltage drop of the DC shunt generator decreases with increasing load for two reasons. They are 1. Armature reaction and 2. Load resistance.
Now you have learned to connect three-phase motor with the starter. Connect a DC shunt generator, field regulator, ammeter and voltmeter. Start the three-phase AC motor. Adjust the field regulator and build up a DC voltage. Determine combined efficiency of the MG set. Hope you had a clear understanding on this technical process. Thank you.
Determine the value of resistance by color code and identify the types.
Hello everyone. Today we will be looking at the process of electrician practical session to identify the parts and terminals of MG set.
Objectives: at the end of this exercise you shall be able to identify the types of resistors by referring to the pictorial representation, identify the color bands and decode the resistance value, calculate the tolerance value by the color band, measure the actual value with an ohmmeter, verify with calculated value. Tools, instruments: multimeter, ohmmeter, 1 number. Materials: variable carbon resistors, dual variable wire wound resistor, wire wound resistors, adjustable wire wound resistor, fixed carbon resistor, preset carbon resistor, fusible resistor, ceramic wire wound resistor. Task 1. Identify the type of resistor from pictorial representation. Identify the resistor's type by referring figure and write the type in table. Sketch the IS symbol for the identified resistor in table. Wire wound resistor, variable resistor, tapped wire resistor, potentiometer, carbon film resistor, preset variable resistor, power resistor, fusible resistor. Task 2. Identify the color band and decode the resistance value. The color bands are read from left to right when holding the resistor so that the tolerance band, if present, is on the right side. If there are 4 bands, the first 2 bands represent significant digits, the third band represents the multiplier, and the fourth band, if present, represents tolerance. Identify the value of resistors shown in figure from the color bands and enter table 2. Identify the first two color bands of the resistors given by the instructor in sequence commencing from the first color band closer to one end of the resistor. Write the first number and second number in table 2. Identify the color of the third band and write the multiplier value in the respective column in table 2. Compute the value of the resistor and record in table 2. Write down the first and second band colors for the respective numbers from the tabulation, so it becomes 50. Then multiply the number with the multiplier of the third band 10, so the value of the resistor is 500 ohms. Identify the fourth band color and fill up the tolerance in table 2. Measure the value of the resistors by using a multimeter or ohmmeter and enter the values. Connect the probes. Connect the red probe to the positive terminal. Connect the black probe to the common terminal. Set the multimeter by ohmmeter. Set the range selector switch to one of the ohm range. Conduct 0 ohm adjustment in analog multimeter. Short circuit the two probes at the selected range. Turn the ohm adjustment knob until the pointer is set at 0 ohm. 0 adjustment. Connect the resistor to be measured. Keep your fingertips off from the probes. Read the meter. Use a range which deflects the pointer to middle of the scale. Read the meter in the ohm scale right above the pointer. Resistance equal to ohm scale reading into magnification at selected range of the resistance range. In figure, the resistance range into 100 is selected. If so, the value of the resistance is 15 into 100 is equal to 1500 ohms is equal to 1.5 kilo ohm. Enter the marked value of resistance and tolerance by the color band over the resistor in table 3.
Now we have learned to identify the types of resistor by referring to the pictorial representation. Identify the color bands and decode the resistance value. Calculate the tolerance value by the color band. Measure the actual value with an ohm meter. Verify with calculated value. Hope you had a clear understanding on this technical process. Thank you.
Hello and welcome to the session on testing of active and passive electronic components and their applications. Let us understand about them. Session objectives. Task 1. Identify the electronic components diode, diode bridge, transistor, SCR and IC by referring to the pictorial representation. Identify the given electronic components diode, diode bridge, selenium bridge, transistor and IC by components through color coding and test the passive components. Task 5. Identify and test the active components. Active components. Active components deliver power or energy to the circuit. These components produce energy in the form of voltage or current. They are capable of providing power. They require an external source for the operations. Examples: diodes, transistors, SCRs, integrated circuits, etc. Passive elements use power or energy from the circuit. These components store energy in the form of voltage or current. They are incapable of providing power. They do not require any external sources for their operations. Examples: resistor, capacitor, inductor, etc. Task 1. Identify the active components. Diode 1N4001, selenium bridge, bridge rectifier 50 ampere, stud type diode, transistor BC547, power transistor, silicon controlled rectifier SCR, light emitting diode LED, integrated circuit IC. Now let us identify the passive components. Resistor, variable resistor, inductor, variable inductor, capacitor, variable capacitor, LDR, light dependent resistor, thermistor. Task 2. Read the symbols for active components in the given circuit diagram. Identify the electronic components given in the circuit diagram. Inductor, label A. Diode, label B. Diode, label C. SCR or thyristor, label D. Identify the electronic components given in the circuit diagram. Bridge rectifier, label E. IC7805, voltage regulator, label N. Diode, label G. Identify the electronic components given in the circuit diagram. Zener diode, label J. LED, label F. Triac, label I. Identify the active components and their base diagram and lead configuration by referring to the data book and component code number. Germanium diode, code number OA79, silicon diode 1N4007, germanium diode AA119, diode BY127, transistor BC147, transistor 2N904, power transistor BD115, N-channel JFET BFW10, thyristor BTY87, diode D3202Y, operational amplifier CA741, voltage regulator CA723, timer IC NE555, NPN transistor SL100, NPN transistor 2N5296, transistor 2N3035, 5-volt relay SN204, N-channel MOSFET 3N187, UJT unijunction transistor 2N2646. Task 4. Identify the passive components through color coding. Let us discuss how to find the value of resistor from color coding. Step 1. Take an assorted number of carbon film resistors with different color codings. Step 2. Hold the resistor with the gold or silver band to the right and read the color codes from the left to the right. Read the colors from the left to right and note down in the tabulation. Step 3. Next, use the table given to see which digits they represent. Usually, the silver or gold color is represented as tolerance. The color next, left to the tolerance is multiplier, and the other two bands are the second and the first digits after multiplier from left. Step 4. Use the color coding table to find the value of resistance. Let us try a trick to memorize the electronic color code. B.B. Roy of Great Britain's Very Good Wife. This is an electronic color code that memorizes the color sequence of resistors. The sequence of the colors should be in order, starting from 0. Black 0, brown is 1, red is 2, orange is 3, yellow is 4, green is 5, blue is 6, violet is 7, grey is 8, and white is 9, as shown in the tabulation. Step 5. Let us find the resistance value for color coding for violet, green, brown, and gold. The first color band is violet, and from the color code table, we can see that violet has a value of 7. The second color band is also green. So now the values are 75. The multiplier is brown, and this color represents 10. If we multiply 75 by 10, we get 750 ohms. The final band, tolerance, is gold. Gold is 5%, which means we can accept resistance with 5% of the error lies from 713 ohm to 787 ohm. Step 6. Measure the same resistance value using a digital multimeter and ensure the measured and calculated values are the same. Turn on the multimeter, set it in resistance mode with the appropriate range, place the probes on both leads of the resistor and note the readings in the tabulation. If no value is displayed in the multimeter or the values measured are more than a deviation from the calculated value, the resistor is defective. Let us discuss how to check the inductor. Take a digital multimeter and set it in resistance mode. Place the probes of the multimeter across the ends of the inductor. The direction of the inductor doesn't matter as resistance has no polarity. If the multimeter shows the resistance is greater than 1, normally less than 10, then it is a good inductor. If the multimeter shows high resistance, then the inductor is defective and must be replaced in the circuit. If the multimeter shows less than an ohm or close to 0, this may be a sign that it's shorted. Outside the range of 1 to 10, an inductor is generally bad. Let us discuss how to test a capacitor. Set the multimeter in resistance mode or at least for 1000 ohm. Place red and black probes of multimeter to the positive and negative terminals of capacitor respectively without changing the polarity. If the multimeter shows some readings and immediately it will return to OL, open loop, or infinity, then the capacitor is in good condition. If the multimeter reading remains constant, then the capacitor is defective. Task 5. Identify and test the active components. Let us discuss how to test a diode. Set the multimeter in diode position or diode check position using selector switch. Place the red and black probe of the multimeter to the anode and cathode of diode respectively, that is forward bias. The multimeter must show some readings for silicon diodes and for germanium. Now, reverse the multimeter probes, place red and black probes to the cathode and anode of diode respectively, that is reverse bias, and the multimeter must show open loop. If the reading matches with table 1, then the diode is in good condition, or else the diode is defective. Let us now discuss how to test a transistor. Testing the NPN transistor. Identify the terminals of NPN transistor, BC547, emitter, base, and collector from the data sheet. Set the multimeter in diode test position using selector switch. Place the red and black probe of multimeter on the base and emitter terminal of transistor respectively, that is forward bias. The multimeter must show 0.7. Reverse the multimeter leads, red and black probes on emitter and base terminals of transistor respectively, that is reverse bias. The multimeter must show open loop. Place the red and black probes of multimeter to the base and collector terminals of transistor respectively, that is forward bias. The multimeter must show 0.7. Reverse the multimeter leads. Place the red and black probes of multimeter to the collector and base terminals of transistor respectively, that is reverse bias. The multimeter must show open loop. Verify the reading with table. If the measured reading does not match with tabulation, then the transistor is defective. Testing the PNP transistor. Identify the terminals of PNP transistor BC557, emitter, base and collector from the data sheet. Set the multimeter in diode test position. Place the multimeter probes between the terminals of PNP transistor as shown in the tabulation and verify the reading. If the readings does not match with the tabulation, then the transistor is defective. Let us discuss how to test an SCR. Identify the SCR TYN616 terminals, anode, cathode and gate from the data sheet. Set the multimeter in resistance mode using selector switch. Place the red and black probes of multimeter at anode and cathode terminals of SCR respectively, forward blocking mode. Note and verify the readings with tabulation. Place the red and black probes of multimeter at anode and cathode terminal with a short between anode and gate terminal of SCR with a small wire. Forward conducting mode. Note and verify the reading with tabulation. If the measured reading does not match with tabulation, then the SCR is defective. Thank you so much everyone for watching this video. I hope you have learned the objectives on testing of active and passive electronic components and their applications. Please do practice this with your instructors. Happy learning!
Namaskar, a warm welcome to all inquisitive audience. Today we are going to have a brief overview on different type of domestic paints available in the market. So first let's start with the introduction of paint. Paint can be defined as a fluid